welcome to Partial Fractions Case 3, the final one in the trilogy, in fact. And often, trilogies end up getting worse as they go on, isn't it? I'm sure you can think of some movie trilogies where that's happened. Occasionally they're all really good. Well, this is one of those cases. Case 3 is equally as good as these earlier lessons on partial fractions. There is a green box hiding what the lesson is about, but that's because I don't want to give away at the moment what's going to happen. That would be a spoiler, wouldn't it? So to start today, I want you to have a go at doing some polynomial division. You should have already be confident, ideally with question 1, that is having a cubic and dividing it by a linear function. But can you divide cubics by quadratics, or indeed a quartic by a quadratic, and things like that? So have a go at number 1. You're welcome to try number 2 and 3 as well. I'm pause the video and I'm going to then go through them. All right, let's do this. So question 1, I'm going to do x minus 3 dividing into x cubed minus x. And you're welcome to fast forward through this bit, to be honest, if you're confident and you just want to check your answer. Okay, let's do this. X's into x cubed go x squared, multiply back through x cubed minus 3x squared, subtract them, that gives us 2x squared. Bring the minus 4x down and repeat. That's going to give us plus 2x, multiply back through 2x squared minus 6x, minus them, minus 4 minus minus 6 gives us 2x, 2x minus 6, x is into 2x, it's 2, so plus 2, multiply back through, minus 6. In this case, we get a remainder of 0, and actually that would help us factorize this cubic if we wanted to. Okay, let's do the next one. I'm going to delete this and start again. Number 2. Now we are doing x squared plus 2x minus 5 into 3x cubed minus 7x squared plus 8x, whoops, that's meant to be an x, minus 7. Note, actually I've not done it here, but note, if for example we didn't have an 8x, then you should leave a gap. Try and sort of have a little place for all your cubes, squares, and so on. You should have sort of seen that before and talked about it, but I'm just going to say it again now. All right, it works in exactly the same way now. It's just going to be a little bit more messy, but we're going to do x squared into 3x cubed and go from there. Just multiply back through by this whole quadratic. So x squared into 3x cubed gives me 3x. So immediately I jump to here. I then multiply back through, and then I'm going to get a plus 6x squared, and then a minus 15x. So you can see it's working in a very similar way. It's just now I've got these 3 terms. These are going to cancel. This is going to give me minus 13x squared, and then I'm going to get a plus 23x. And then I'm going to bring down my minus 7. X squared into minus 13x squared go minus 13, multiply back through, minus 13x squared minus 26x plus 65. Okay, minus them, that's going to give us 49x minus 72. And actually that's it, that's all we can do. I'm just going to check my answer. Yeah, good, I got what I got before. We've actually got a remainder that's not just a number now. It involves x as well, and that's just how it is. And what that actually means is that this thing here, if we wrote it x squared plus, hold on, I'm doing it the wrong way around. This thing up here, 3x cubed minus 7x squared plus 8x minus 7 all over x squared plus 2x minus 5. That actually equals 3x minus 13. And then what happens to this remainder? Well, you just have it, and then you still need to divide it by this x squared. I don't know why I put 2 copies in there. And that's it. So we can actually have this cubic divided by a quadratic. We get this linear function, and then we're left with this thing here. Now, why would I want to do that? I guess it's a bit of fun, isn't it? But also, it does have some uses. Again, I'm not going to talk loads about the uses, but I am going to talk about one use today. And that is if, for example, I asked you to sketch the function on the left here, this cubic divided by a quadratic. You might think there's no way I ever want to sketch that, and I think you'd be right. But you can obtain some good sort of ideas. Sorry, what am I trying to say? You can obtain some information about what is going on, even if you can't sketch the whole thing. We can get little bits of information. For example, what happens is x tends to infinity. Well, it's going to approach infinity here. We can see because the cubic approaches infinity quicker than the quadratic. But how is it going to approach infinity? And that is something we can actually get by looking at this form here quite quickly. Because as x tends to infinity, this thing is actually going to tend to 0. Because the quadratic on the bottom is now going to dominate. So as x tends to infinity, this function here will tend to 3x minus 13. So this graph is, I don't even really know what it's going to look like, but as x gets really big, it's actually just going to start behaving a bit like a linear function. And I think that's quite interesting. It's something, yeah, something worth thinking about. And we could get other points. If you again, I could find out where this what happens when x is 0. I could think about what happens when x is when x is minus infinity. The same thing's going to happen, isn't it? So when x is minus infinity, this is still going to tend to 0. So I'm still going to get 3x minus 13, and I think it's going to go down here like this. So something's going on here, who knows what, but I do understand by doing this division what's going on at these extreme values. Okay, I'm just putting that out there. Good little thing to think about. Right, back to polynomial division, this last one. I think at this point it'd be really great if you try number 3 if you haven't tried any of them already. It's working in a similar way, but now I've got a quartic divided by a quadratic. Right, so it's going to be x squared minus x minus 2 goes into x to the 4. Well, it's definitely something that you could be asked. Just a stand-alone question. Work out the quotient, that's the number you get at the top, and the remainder, that's the thing you're left with at the bottom. You know what, maybe you've never, I'm sure you would have seen these before, but the quotient is up here, and the remainder is what is left over. I'm just going to write those down. 2x squared minus 11x minus 15. What about you? I really just enjoy doing a bit of polynomial division here and there. Right, so x squared into x to the 4 go x squared, multiplied back through x to the 4 minus x cubed minus 2x squared. Subtract these, that's going to give me 3x to the 3 plus 4x squared. Bring the 11x down. X squared into 3x cubed is going to be plus 3x, multiply back through, minus 6x. Subtract them, we're going to get 7x squared minus 5x. And then finally, I bring down this minus 15. X squared, I'm going to get plus 7, 7x squared minus 7x minus 14, nearly there. That's going to give me 2x minus 1. So I've got my remainder, I've got my quotient, and I could write this function down, that this thing divided by this thing as x squared plus 3x plus 7 plus, so this is just an extra little bit I'm doing, plus this divided by x squared minus x minus. So I could again now think about what's happening with the extreme values. And that's it. That's a bit of a reminder of polynomial division. Okay, onwards. So why have I called this partial fraction case 3? What has this got to do with it? Well, we'll find out in a second. Okay, question. Split this thing here on the left into partial fractions. How would we do it? Well, previously, I taught you that this kind of thing, to write it as equivalent to a over x minus 1 plus b over x minus 2, didn't I? I was like, yeah, this is what you should do. It falls apart here. Why does it fall apart? Because there is no way that I could add fractions with constant coefficients together and get an x squared up here. So you can do this method and you can get a value for a and b using our substitution, but it won't actually be correct because you've made an incorrect assumption. So no longer, some of pen's given up on me, no longer works. Why does it no longer work? It's because the order of the numerator is equal to 2. The order is like the highest power, and the order of the denominator is also equal to 2. This was not the case for all our previous partial fraction cases. It was always just an x is in there and a constant. The order was always less than the numerator order was always less than the denominator order. So today's lesson is partial fractions case 3, when the degree of the denominator is less than the degree of the numerator. Actually, I think that's the degree of the denominator is less than or equal to. Sorry, there should definitely be a less than or equal to in there. If the degree of the denominator is greater than the degree of the numerator, then you're going to need to know cases 1 and 2. But if they are the same, or actually the denominator is less than the numerator, we need another method. What is that method? Well, it's going to be a bit of polynomial division. So let's do this. We are first going to have to take this and do some division. So it's going to become 3x squared minus 3x minus 2 all over x squared minus 3x plus 2. Now I could do a division by x minus 1 and then by x minus 2, but it's going to be much quicker to just do it all in one go. So I'm now going to do this into this. This is basically what we're doing at the start of the lesson now. Okay, x squared into 3x squared go 3. Multiply back through 3x squared minus 9x plus 6. Minus them, I'm going to get 6x minus 8. What I can do, if you're paying attention to my to what I wrote above, is that this thing here, okay, I'm just going to put it in a bracket actually. This thing here is going to equal 3 plus 6x minus 8, that's my remainder, divided by this thing here, which I'm now going to rewrite in factorized form. So there's one extra step needed. Do a division, get this sort of number by itself, could be a number and an x and other things, and then get something where the degree, I think I called it the order, didn't I, before? I'm sorry. I'm sure it's the same thing. let's revert to degree. The degree of this is 1 because it's you've just got an x. Now the denominator is more than it because it's a degree of 2. So we can use our normal partial fractions on it. Okay, so now use normal partial fractions. And do you know what? I don't think I'm going to do that here. Like, you know how to do that. This is, in this particular case, it's case 1. And I just think it's me wasting time, your time and my time, if I go back through doing case 1. Just done it. But that is how we can split something into partial fractions which has a numerator that has a degree greater or equal to the denominator. Okay, so just a very quick recap. We've done quite a lot today. We've done polynomial division when it's not just an x that we're dividing by. Could be an x squared, could be an x cubed, but it's the same idea. Try to illustrate that. We've then looked at splitting something into partial fractions where the degree is greater or equal to that of the denominator. I did one where it was equal to, but it would be the similar if it was greater than. And then we end up with a partial fraction from earlier on that we've covered, and we could, in theory, deal with that as well. I just very quickly want to, I don't know if it'll actually be that quick, but I want to talk about sort of typical questions that you could be asked, because this is it actually. You might not just be told, write it in partial fractions. They might give you a bit of a hint, but they might write it a bit like this. Given that this thing equals ax squared plus bx plus c plus d over x minus 3, find the values of a, b, c, and d. You could also get asked it in this way. And I want to just talk about a few techniques that you can use to do this. So, technique 1 is going to be to do a division. X minus 3 into x cubed. Haha, this is one of those now where I am missing an x. So I'm actually going to write 0x and line it up nicely. Okay, and then I'm going to do my division. Let's do it again. So we get x squared, multiply back through, subtract 4x squared, bring the 0 down, plus 4x, multiply back through, 4x squared minus 12x, subtract. See, that's why it's important to have this 0x, just so I just think it makes it a bit more, bit less likely to make mistakes. Bring the 7 down, plus 12, 12x minus 36, and that's going to give us 29. So what does that mean? That means that x cubed plus x squared minus 7 all over x minus 3 is actually equal to x squared plus 4x plus 12 plus 29 over x minus 3. And I've actually solved it just by doing this division. I can just look at it and I can think, right, well, a is clearly going to equal 1, b is going to equal 4, c is going to equal 12, and d is going to equal 29, and I'm done. So the way it's written here kind of, kind of implies that, like, I mean, when they write it like this, it kind of indicates to you, yeah, do a division. Actually, it probably doesn't indicate it, but what I'm saying, okay, is that you can quite quickly do a division and you can just get it all super fast. We split it into partial fractions. I think this is still called partial fractions. I mean, technically we've only got this one fraction over here and then we've got this quotient, but that is a good method that you can use. Now, it's going to be harder to spot that on the second one because they've not written it in the form of a division. So you would have to realize that you can divide both sides by x minus 3 and then do your division. So you'd have to spot that. Note, you could be dividing by a quadratic, and maybe, again, you'll get something over here that you'll then need to do your normal partial fractions on. So there's so many ways this can be asked, and it's a case of practicing and making sure you've understood it. That was technique number 1 anyway. Technique number 2. Right, let's imagine that it's the second question, because I think the way the first question's written kind of shouts out to me polynomial division. But let's imagine you don't spot that, and you either are given the first question and you times through by x minus 3 to give this second part, or you're just given the second question. How could we otherwise find A, B, C, and D? Well, we can revert back to our normal partial fraction techniques. We can do a substitution. So let x equal 3. That's the one that shouts out to me because that will make this equal to 0. Then we're going to get that 27 plus 9 minus 7 is equal to D because this disappears. And therefore D is equal to 29, which is what we got before, and we've managed to calculate it. How can I do some of the other ones? Well, something else that jumps out is to look at the coefficients. So I'm now just combining different techniques to help me. Let's look at the coefficient of x cubed. We're going to get that 1 on the left-hand side must equal a, because this is the only way I can get an x cubed on the right-hand side, by doing ax squared times x. So I've managed to find my a. What else should we do? Let's do the coefficient for x squared, because that's not going to be too bad. It's going to be a little bit more complicated. So 1 on the left-hand side, then I'm going to work in red now. Right, how can I get an x squared on the right-hand side? Well, I could get it by doing minus 3ax squared, so it's going to be minus 3a. I could also get it by doing plus b, and that is the only way. So I'm going to get that 1 is equal to minus 3 plus b, and therefore b is equal to 4. Finally, if I want c, I could do a coefficient of x. That would work, but I think I'll do another substitution now, because I think that'll be a bit quicker. So let x equal, a sensible one would be 0. So I'm going to get that minus 7 equals, now when I put 0 in, this is going to go, this is going to go, I'm going to be left with c, and then I'm going to multiply that by 0 minus 3, and then I've still got to add my 29 from d. So I can subtract 29, and I'm going to get minus 36 equals minus 3c, and so c is going to equal 12. And I've managed to get the coefficients in a second way. I think I got the same ones. Good, yeah. So this, I'm really hoping I haven't confused you here. This lesson is about using division to help us if we can spot it. It's about using the techniques of substitution and looking at coefficients, and it's basically just developing a fluency for deciding which one to use and which makes it the most effective. I think the way I've done it here, if I don't do polynomial division, because I think division is the quickest way, is a good method. So that is it. That is our last case of partial fractions, and we are going to find later on just how useful it is, a tool for being able to do mathematics as well as interesting in its own right. So thanks for watching this trilogy. There won't be a fourth lesson on partial fractions. You'll have to cover that, I think, in further maths if you're studying it there. I'm just going to mention, actually, I can't quite help myself. So what if you get something like 1 over x plus 1, and then you have maybe an x squared plus 9 in there? How would you rewrite that in part? I've just made this question up, so I have no idea how nice this answer is, by the way. But how could you split this into partial fractions? That's something that goes a bit beyond what we cover in A-level. But we've covered quite a lot, especially with the extension questions involving cubes and squares and all sorts, really. So I'm happy how we've done. Okay, that's it.